Here we discuss additivity theorem on integration. The theorem is this. Let f is a function from AB to R and C is any point in between A and B. Then f belongs to RAB if and only if its restrictions to AC and CB are both Riemann integrable and in this case integral A to B f is equal to integral A to C f plus integral C to B f. So let us try to prove this result. First we prove the converse. That is, suppose the restrictions of f to AC and CB are both Riemann integrable. Then we have to prove the function f is Riemann integrable on AB. So let the restrictions of f to AC and CB be Riemann integrable. With the integrals L1 equal to integral A to C f and L2 equal to integral C to B f. Then by the definition of Riemann integral, for a given epsilon positive there exists delta positive such that if P1 is any tagged partition of AC with the known P1 less than delta, we have modulus of SFP1 where F is actually the restriction of F to AC. Minus L1 is less than epsilon by 3. Take it 1. Similarly, there exists delta dash greater than 0 such that if P2 is any tagged partition of CB with the known P2 less than delta dash, we have modulus of SFP2 minus L2 is less than epsilon by 3. Number 2. Let m equal to maximum of modulus of fx. Now define d equal to delta. You take delta one equal to, or let it be delta epsilon equal to minimum of delta dash and epsilon divided by 6m. Let P be any tagged partition of AB with the norm P less than delta. We will prove that modulus of S of P minus of L1 plus L2 is less than epsilon, so that the function f is Riemann integrable on AB with integral L1 plus L2, that is integral A to C f and plus integral C to B f. Now this P, the partition of AB, let it be of the form some ik with the tags tk. K is equal to 1 to m, where each ik is the interval xk minus 1 xk. Now there are two cases. Since C is the point in between A and B, this C may be sometimes a partition point, one of these xk, or maybe inside some interval like this. So let us take the case 1. Let us see be such that a partition point of P. Now split P into P1 and P2 of partitions AC and CB respectively. That is, we are splitting the partition P as P1 and P2, where P1 is a partition of AC and P2 is a partition of CB, and P1 union P2 will be P. In that case, we can see that in this case we see that the Riemann sum corresponding to P of F will be the same as S of P1 plus S of P2. And each P1 and P2 are with the norm that of P. If it is assumed less than delta epsilon, that is less than delta dash or epsilon by 6 sum, because delta epsilon we have assumed the minimum of delta dash and epsilon by 6 sum. So if P is assumed a tagged partition of AB with norm P less than delta epsilon, this P1 and P2, the tagged partitions of AC and CB will be with the norm P1 less than delta and norm P2 will be less than delta dash, and therefore we have S of P1 minus L1 is less than epsilon by 3 and S of P2 minus L2 is less than epsilon by 3, and since S of P is S of P1 plus S of P2, we have actually modulus of S of P minus L1 plus L2 is less than epsilon by 2 epsilon by 3. Let us check that. So since P1 and P2 are, if P is a tagged partition of AB with norm P less than delta epsilon, then it is very clear that P1 and P2, the tagged partitions of AC and CB respectively, are such that norm P1 less than delta epsilon, which is less than delta, and norm P2 less than delta epsilon, which is less than delta dash. So in any of these cases, we have S of P1 less than L1 less than epsilon by 3, S of P2 minus L2 less than epsilon by 3. We have modulus of S of P1 minus L1 is less than epsilon by 3 and modulus of S of P2 minus L2 is less than epsilon by 3. Hence, modulus of S of P minus L1 plus L2 we can write as S of P by S2, it is S of P1 plus S of P2. So S of P1 plus S of P2 minus of L1 plus L2, which is clearly less than or equal to modulus of S of P1 minus L1 plus modulus of S of P2 minus L2, which is less than epsilon by 3 plus epsilon by 3, it is clearly less than epsilon. So in that case, we have integral A to B F is equal to integral A to C F plus integral C to B F, with the F in RA. Now let us take the case 2, where C be not a partition point, but let C be in some xk minus 1 xk for some k. In this case, let P1 be the tagged partition of AC defined by P1 is equal to I1 T1, I2 T2, etc. I k minus 1, Tk minus 1. Then the interval xk minus 1 C with the tag C, the last. and P2 be the tagged partition of CB, where P2 is given by P2 equal to first C xk with the tag C, and the remaining are ik plus 1, tk plus 1, ik plus 2, tk plus 2, etc. im tm. Then it is very clear that S of Q, P if you find, S of P if you find, S of P minus S of P1 minus S of P2 will be equal to since S in the SF the contribution towards some S of P and that of S of P1 are common except for the last interval Sk minus 1C, and similarly the contribution to S of P from CB and S of P2 differ only by the terms corresponding to the first interval C xkc of P2, and therefore S of P1 minus S of P1, S of P minus S of P1 minus S of P2 will be only the difference f of tk into xk minus 1, that is corresponding to the sum S of P minus fc into xk minus 1. All other terms get cancelled because all the terms are the same, that of S of P1 and that of S of P2 and S of P. Many terms except these two terms are the same, and therefore S of P minus S of P1 minus S of P2 will be ftk into xk minus 1 minus fc into xk minus 1. And therefore modulus of S of P minus S of P1 minus S of P2 will be equal to modulus of f of tk minus f of c into xk minus 1, which is clearly less than or equal to modulus of f of tk plus f of c into modulus of xk minus 1, and this is clearly less than or equal to m plus m, because m we have taken as the bound of f of k. So mod of f of tk, mod of f of tk is less than or equal to m, and mod of fc is also less than or equal to m. And modulus of xk minus 1, which is clearly less than delta epsilon, so which is equal to 2m into delta epsilon, and this is clearly less than epsilon by 3, since we have taken delta epsilon as minimum of delta dash and epsilon by 6m, and therefore epsilon by by 3 plus epsilon, 2 epsilon by 3 is clearly less than 2m into delta epsilon is clearly less than epsilon by 3, since epsilon delta epsilon is equal to minimum of delta dash and epsilon by 6m, that is delta epsilon is less than epsilon divided by 6m, from this 2m into delta epsilon is less than epsilon by 3. Also we have P1 and P2 are such that norm of P1 is less than delta, norm of P2 is less than delta. Since they are respectively less than delta 1, delta and delta double dash. So norm of P1 also norm of P1 is less than delta epsilon, which is clearly less than delta, and norm of P2 is also less than delta epsilon, which is less than delta dash, and therefore we have modulus of S of P1 minus L1 is less than epsilon by 3, and modulus of S of P2 minus L2 is less than epsilon by 3 by the condition we have in 1 and 2. So we have modulus of S of P minus S of P1 minus S of P2 is less than epsilon by 3, and mod of S of P1 minus L1 is less than epsilon by 3, and modulus of S of P2 minus L2 is less than epsilon by 3. So combining all these things, we can see that modulus of S of P minus of L1 plus L2 is clearly less than epsilon. This you can verify, which shows that F belongs to RAB with integral A to BF is equal to L1 plus L2, which is equal to integral A to CF plus integral C to BF. So this is the first part, the converse of the theorem. Now we have to prove if F from AB to R is Riemann integral and C is a point in AB, we have to prove its restrictions to AC and CB are both Riemann integral. Now suppose F belongs to RA. And let epsilon greater than 0 be given. Then by Cauchy's criteria, there exists some delta epsilon greater than 0 such that if P and Q are any tagged partition of AB with the norm P and norm Q less than delta epsilon, we have modulus of S of P minus S of Q is less than epsilon. Now we have to prove. So let this be some 1. We have to prove its restrictions. The restrictions of F to AC is Riemann integral and the restriction of F to CB is also Riemann integral. First we will prove the restriction of F to AC. Then we will prove the restriction F1 of F to AC is Riemann integral. Let P1 and Q1 be the tagged partitions of AC. With norm P1 less than delta epsilon and norm Q1 P1 and Q1 less than delta epsilon. So this is the thing we have. So point C is B. So we have taken two tagged partitions P1 and Q1 of AC with the norm P1 less than delta epsilon and norm Q less than delta epsilon. Now extend this P1 and Q1 to the whole interval AB by adding same partition points and tags of CB. So you take some partition CB here, then you add the same partition points and tags to P1 and Q1, and thereby we are getting P and Q. So extend this P1 Q1 to AB by adding same partition points and tags of CB. Let P and Q be the partitions so obtained, partitions of AB so obtained. Here we have taken such a way that P1 and Q1 are extended to P and Q with the norm P norm Q less than delta epsilon. Let P and Q be the partitions of so obtained, keeping with the condition that norm P less than delta epsilon and norm Q is also less than delta epsilon. Now, by the hypothesis we have, since F is in RAB, we have modulus of SFP minus SFQ is less than epsilon. But modulus of SFP1, SF1P, P1 minus SF1Q1 is the same as SFP minus SFQ, since we have added the same partition points and tags to P1 and Q1 to get P and Q. So that get cancelled. So modulus of SFP1 minus SF1P1 minus SF1Q1 is clearly the same as modulus of SFP minus SFQ, and hence this is also less than epsilon, and hence F1 belongs to RAC. Similarly, by extending the partitions of CB to the whole interval AB by adding same partition points and tags from AC, we will get the two partitions of AB, and for that also we will have this condition modulus of SFP minus SFQ less than epsilon, and that way we will get modulus of SFP2 P2 minus SFP2 Q2 will be the same as modulus of SFP minus SFQ, which is also less than epsilon. So similarly we can prove F2, the restriction of F2 CB is also Riemann integrable. that is F2 belongs to RCB. And moreover, we can easily verify that integral A to CF will be equal to integral A to BF will be equal to A to CF plus integral C to BF by the first part of the theorem that we proved. There we proved that if the restrictions are Riemann integrable, restrictions of F to AC and CB are Riemann integrable, and F is Riemann integrable, and integral A to BF is equal to integral A to CF plus integral C to BF. Hence the theorem. So this theorem is widely used in calculus for the calculation of integration. Thank you.